is formulated from going from whatever the length of this one, pretty much, right, is in terms of coordinates, x coordinate A and y coordinate B. And if we integrate this cross-section along with this delta x, now in Riemann sum notation delta x, and here integral notation of dx, this becomes a volume, right? So looking at the solid here, and you can imagine that you can put different cross-sections, right? I put some odd cross-section, not perpendicular or anything, some bizarre cross-section there, axis of cross-section. I'm going to call that z something. And you can imagine we have a different cross-section formula. Therefore, you can have a volume of the same thing going from, let's say, C to D. Now it's a different cross-section function, so I'm going to use BZ. You can imagine, right? If you slice in a different way, and it has different shape, right? So that BZ along the DZ will be the approximation of the volume, right? Maybe to every people or physicists and engineers, the reason these two things are being equal to each other is obvious. There's a solid, you compute the volume one way or another, you're supposed to be the same thing, right? But it turns out in mathematics, you have to define the volume first before you actually justify any claim. You got to give a foundation. You have to properly define the volume, which we won't do. But we did that for the area, right? How did we define the area underneath the curve? The limit of a Riemann sum, that was the definition. That was an approximation. That was the definition of area. They do the similar thing to the volume, okay? And justifying these two things being equal to each other turns out to be major work. Turns out it's not easy. It's not that I'm looking at the same solid this way, that way. Of course, volume should be the same. But if you ask this why, chain of why, you easily get puzzled. What is the bottom of the chain of reasoning is the definition of the volume. If you stick to the definition of the volume, it turns out showing these two things are equal to each other is not that simple. Okay? So that result is called Fubini's theorem. Fubini's theorem. I have a proof of a lengthy discussion of this Fubini's theorem for Calc 3 students, but I'm going to share it. If you'd like, you can take a look, but it's quite boring, and you don't have to read it if you're not interested in mathematics. That part of the mathematics. All right. So this is now obvious to everybody. Of course, volume calculated different way should be the same, but two mathematicians know, and then it's called Fubini's theorem. Okay. But you can imagine one cross-section is more convenient than the other. So that was a review. We didn't actually do the two different method, but this part's new actually. I throw in two different things. All right, next.